Now, if we go to section 3.5.2 of the code, you'll find we have 4 classes of steel sections. These sections has been arranged from the most strong one to the least one, or to the weakest section. So the first is called plastic section. This is under class 1. One of the behavior of this plastic section is that under loading, or when they are subjected to loads, they tend to develop a plastic hinge. And in the elements which are subjected to compression should meet the respective limits that are given in table 11 or table 12 of the same code that I have mentioned to you. The second class is called the compact section. So in this case, we say these sections develops plastic moment capacity. Again, classifications limits for this class can also be referred to either table 11 or table 12 of the code. Later on, we shall look on the contents that has been given in these 2 tables. We shall see the difference between table 11 and table 12 respectively. So that is the second classification, which is called the compact section. The third one is called the semi-compact section. Semi-compact section. So the structural behavior of class 3 is that when they're subjected to stresses, the extreme fibers which are under compression, normally they reach the design strength. But while the design strength is reached, the full moment capacity cannot be developed. So they can withstand sufficient compression resistance or compression stresses, but they cannot reach the plastic moment capacity. That means no plastic hinge is formed when the section is subjected to loads. Like section 1 and 2, section 3, or sections that fall on class 3, they should also meet all limits as given in table 11 and table 12 respectively. The last section, which is section 4, this one is slender sections. So this one, designing on this one, then we should ensure a sufficient allowance to take into account the effects of local buckling. Because class 4 sections, these ones, they are all slender. And again, the elements that are subjected to compression, These ones do not meet limits for other classifications. That they are beyond classifications classes 1, 2, and 3. But they are defined as slender sections. This means that if you take your section, then you consider the sectional properties that we initially discussed, and you go to table 11 or table 2, and if you find those limits are not met, it means your section will automatically fall under class 4, which is slender sections. So let's look on table 11 and table 12, where we can have a clear picture of what we are talking about. So I think you can see the table 11 here, right? Do you see table 11?
No.
You don't see?
No.
Yes? It is on your, what do you see on your screen?
The page with class 3 and class 4 notes.
Okay, let me show you now. I think now you can see it, right?
Yes.
Yeah, so this is table 11. So you see here, this table 11 deals with classifications of all sections that are not circular hollow section or rectangular hollow sections. So it classifies all sections that are not circular hollow sections and rectangular hollow sections, right? Do you see the screen?
Yes.
Okay. Now, and recall the various section properties that we discussed earlier. Now, on this column, on the first column, we have the compression element. That means on the section, here we have first to consider the section element, which is under compression. Okay, and again, we have here, we have the rolled section, we have the welded section. Okay, we may have compression due to bending, because in other structures, we shall have the compression forces also, which will induce bending, like in column sections. Column sections are subjected to compression, right? But the compression forces also induces some bendings. And in this row here, we have total axial compression. Okay, and if you look here, we have outstanding element of compression flange. And then you have internal element of compression flange. So the difference between the two, we shall see them later. But for example, suppose we want to classify a beam section. Now, a beam, we know this is the flexural member. And under loading, we expect that the upper part will be under compression and the bottom part will be subjected to tension, right? Now, the top flange, which is subjected to compression, okay? So what we have to find, one of the properties that are used in classification is the ratio between the flange width to the flange thickness. Okay, so you find the ratio between B and T. Now, if you find the ratio of B, which is the compression flange width, and T, which is the corresponding flange thickness, if this ratio does not exceed 9 times epsilon, then that section is classified as plastic in terms of compression. The ratio epsilon here, you can see here, you see, this is the meaning of the parameter epsilon. Do you see it? This is the square root of 275 divided by what? By the design strength. It's under root. You get the parameter epsilon. Do you see this one?
Yes.
Yeah. So you have to find that ratio, which is B divided by T. And make sure you really know your section, whether it's rolled or it is welded. If it is a welded section, then the ratio between the flange width and flange thickness should not exceed 8 multiplied by epsilon for a section to be classified as plastic in terms of its flange. Right?
Yes.
Yeah. So, however, if you find this ratio is greater than 9 multiplied by epsilon, but less than 10 multiplied by epsilon, then your section will not be plastic. Instead, it will be compact. Okay?
Yes.
Again, if you find the same ratio is greater than 10 multiplied by epsilon, but less than 15 multiplied by epsilon, your section will not be plastic, will also not be compact. Instead, it will be semi-compact. Okay?
Okay.
And if you find your section with respect to its flange, when we consider the rolled section, if we find the ratio between B and T is greater than 15 multiplied by epsilon, then your section will neither be plastic, compact, nor semi-compact. Instead, it will now be slender section. So slender sections that are class 4, although they are not mentioned in table 11, then if they can be defined by considering these ratios. If you find the ratio between these ratios are beyond these limits, then your sections will automatically fall into slender sections. However, in design, slender sections are not recommended. Okay? So when you make a design, do not design the section that is slender. Instead, make sure you either design between range, class 1 into class 3. So this is with respect to flange. Now, after classifying the flange, then you come to web section. You see, this is the web section. Web section. Now, normally, for a beam section, for example, the neutral axis lies at the mid depth. Okay, so if we classify a beam section, we shall consider here that is the neutral axis is at the mid depth. Now, if the neutral axis is the mid depth, then we now define the depth of the web divided by the thickness of the web. Small t here stands for the thickness of the web. And these are ratios. If d over t does not exceed 80 times epsilon, then your section will automatically be plastic. But if 80d is less than, sorry, 80 times epsilon is less than the ratio d over t, then it does not exceed 100 times epsilon, then automatically your section will be compact. And if 100 times epsilon is less than d over t, but less again than 120 times e, automatically your section will fall under semi-compact. But if 120 multiplied by epsilon is less than d over t, automatically your section will be slender 1. Okay? So for this one is a peculiar case for compression members. Or you can say, after looking on this one, then generally you can also consider these ratios. But this one is more specific for the column sections. We shall see later. And this one is for the channel section. This one, the classification due to angle sections, compression due to bending. Okay. This one is for single or double angle with the components separated. We shall see later these ones. But all in all, these they are classifications limits for all sections that are not circular hollow sections or rectangular hollow sections. And this one is with respect to table 11. Now, if you look on table 12, you see, this is the table 12 now. This is the classification criteria. This one is the classification criteria for circular hollow sections and the rectangular hollow sections. This one is table 12 of the code. Okay, so this one is for circular hollow sections, of which can be subjected to bending or to compressions. And these one are the ratios. Okay, this one is for rectangular hollow sections. Okay. So here, HF stands for hot finished, and CF stands for cold deformed. So here you have hot finished rectangular hollow section, and here we have cold finished rectangular hollow sections. These finishes are with respect to production process. If they are produced under hot condition, so they fall under the category which is called hot finished rectangular hollow sections. But if they are formed under cold conditions, then they will be called cold deformed rectangular hollow sections. But if your sections are universal beams, universal columns, channels, angles, T's, these ones are classified with respect to table 11. Okay? Question to that point? Clear? Okay. So if it's clear, then let's move forward to another part. Okay, do you see the screen, lecture 2?
Yes.
Okay. So after an introduction part, of which we looked on the definitions regarding the structural steelwork, the structural elements that can be formed by the use of steel. We looked on various steel sections. We looked on the basic properties for structural steel design of these steel elements. And finally, we looked on the overview on structural steel classes that will be applied in our future sessions. Then now let's look on the second part, which is the design philosophy of structural steelwork. So first of all, let's look on the scope of the structural steelwork. Structural steelwork, as far as its design is concerned, involves 4 major steps. The first one is the estimation of loads. Okay? We have to predict type, magnitude, and the locations of all loads that will be resisted by these steel elements. Okay? We have to determine the type of loads, their corresponding magnitude, as well as the point of locations on a particular structural steel element, whether it's a beam, the column, truss, or any other structural steel element. Now, after knowing the magnitude of those loads, we have now to determine their effects in terms of stresses that they induce when those loads are subjected to these structural elements. That step is what we call structural analysis, which is intended to determine the internal forces. The internal forces, these are their stresses. Now, common stresses that are used in design involves the bending moments, the shear, as well as the normal forces. So all this has to be determined as the results of application of loads on a certain particular structural steel element. Now, with the information obtained from stress analysis, then we can now design our structure. So the design, this one involves determination of appropriate cross-section or selection of a suitable cross-section. And then we shall also have to determine and design the proper connection to be used to connect various members that meet at a certain point. So that's a process which involves member section selection, and the detail of connections is what we call structural steel design. And this one depends very much on analysis. So if the analysis is wrong, automatically your design will also be incorrect, right? Then after that, the next step is now production of the structural drawings. Or in other literature, you'll find them, they're simply called working drawings. So once your design is complete, then you have now to produce the working drawings. So these ones, they will now be used for budgeting and overall structural fabrication. Okay. However, the working drawings should have or should consist all necessary informations that are required for the production team to carry out properly their job. Okay? Clear?
Yes.
Yes. So let's have a 5-minute break, then thereafter we shall proceed, right? Okay, thank you.
Yes.